Hi, this is problem 9.20, and it's a problem about beam deflection. And it says determine the reaction at the roller support. So we notice that there's a roller support here, which will only have a force normal. And then here, though, we have another 3 reaction forces in this direction, and this direction. So this is statically indeterminate problem, because we will have 3 equations, the static equations, and then we'll have 4 unknowns. So here's what we're gonna do. We're gonna replace A, the reaction at A, with the force, RA, and then pretend that we know that, and just keep going and do our problem. So here's what we're gonna do. If we cut right here, we're gonna get what? Well, let's draw what we would have. We would have, and I might need a little more space here. So we would have the reaction force at A, RA, and then we have this distributed load on top. And then we would have this distance, which is an X, because we don't know what distance that is. And we cut, so we'll have a V1 and an M1. Now, we don't really care about the V1, so let's just go with the M1. So M1 is going to be what? Well, we have the reaction at A that makes us smile, makes the beam smile. So that's going to be RA times X, because it's at a distance X. And then we have the W that doesn't make us smile, so that's negative. And it's going to be W times the total distance X. That gives me a force at a distance of X divided by 2. X divided by 2. So we can say that M1 is equal to let me keep the color coding for you guys, RA times X minus W times X squared divided by 2. Okay? Well, now what do we do with this? Well, now we remember that there's this deflection formula that's really a relationship, and that's the second derivative of y with respect to x gives us the moment as a function of x. So what can we say? Well, we have our moment equation, right? So that's going to be RA times x minus W times x squared divided by 2. Okay, so now we can integrate both sides with respect to x. So I'm going to integrate this left side, and I took E and I out because I'm assuming they're constant throughout x. And here we're going to integrate and distribute the integral. So we'll say RA is constant, and then we have x dx minus W over 2. Those are both constants. And then here we have x squared dx. Now, I think it's important to realize that I can say W is constant because it's a line. Otherwise, I'd have to have W as a function of x, and I would not be able to pull it out of the integral. So here on the left-hand side, we get EI dy dx. On the right-hand side, we get 1/2 RAX squared minus 1/6 W x to the third plus constant 1. Now let's integrate one more time. So I'm going to rewrite this. And I'll pull these out again because I'm assuming they're constant along the x-axis. And then I will pull out these again. W is constant along the x-axis as we see from the drawing. And then we'd also have the integral C1, which is a constant. So I can pull it out of the integral. Okay. So now we get E, I, y as a function of x is equal to 1/2 RA times 1/3 x. Well, let me just make sure I'm not. So if I take the derivative of this, what do I get? Well, I get 3x squared. So if I have an x squared, what I want to do is I want to go back here. I'm going to do 3 divided by 3x to the third, right? So yeah, I'm going to have 1/3 x to the third minus, the constants, I'll all add them up to the end, minus 1/6 w times 1/4 x to the fourth, and then we have plus c1x plus c2. So let's simplify this expression a little bit. We have 1/6 RA x to the third minus 1/24 w x to the fourth plus c1x c2 plus c2. So how many unknowns do we have? Well, we're trying to find the reaction at the roller, and we have some initial conditions that we can use. So let's get rid of C1 and C2 first. Well, let's look at our drawing. We know right here, what can we say? Can we say the slope is 0? No, because it's not constrained that way. But we can say our y is 0. So at x equals 0, our y is equal to 0. Here we can say at x equals L, our y is equal to 0, and our dy dx is equal to 0. So let's write them down here. Our boundary conditions are 0 at x equals 0, y equals 0. At x equals L, y is equal to 0. And at x equals L, dy dx is equal to 0. So that gives us 3 equations. So we have the equations for statics. So that's 6 total equations. And how many unknowns do we have? We have 1, 2, 3, and 4. Assuming that we know EI. Okay? So we can start, I'm going to start with the slope one here. If I take this equation, copy, paste it, I can say that, I can say that 0 here, because I plug in this, happens when we have 1/2 RA L squared minus 1/6 WL to the third plus C1 And so I can say C1 equals to 1/6 WL to the third minus 1/2 RAL squared. Let's see if we can do some algebra. Well, we can pull out, we can pull out 1/6 and L squared, and we'd be left with WL minus 3 RA times 3. Sorry. Oh, it's not exactly like that. RA times 3. So let me check. If I multiply back out, seems like it's gonna work. Okay, so that's my C1. So then I say, I can plug that back into the final function. So that would be this one right here. And so let me put that in here. Plug that back into this function at C1. So that would be plus 1/6 L squared times WL minus RA times 3 X plus C2. Now, what do we know about C2? Well, we can say 0, 0. So when this is 0, all of these terms go to 0, and we get C2 is equal to 0. So now we can rewrite this expression without the C2. And now we have one more to feed in, which is that L, y is 0. When x is equal to L, y is 0. So at 0, we have RA over 6 times L to the third minus 1/24 W times L to the fourth plus 1/6L to the third WL minus RA times 3. And so now we know L. We can solve for RA. Or we can solve for W, depending on what we know, what we don't know. And so how would we do that? Well, let's simplify this a little bit. RA over 6 L to the third minus 1/24 WL to the fourth plus 1/6 L to the fourth W, or WL to the fourth, minus 1/2 RAL to the third. So these are similar. So we can add them up, and we're going to get, 1/2 is the same thing as 3/6. So 1/6 minus 3/6 is minus 2/6 RAL to the third. And then 1/6 is the same thing as 4/24. So that we're going to keep my positive 3/24 WL to the fourth. And that would be 1 and 8. So now we get 0 is equal to minus 2/6 RAL to the third plus 1/8 WL to the fourth. And so now we get, bring the first term to the other side. And then, how did I get did I not simplify to 2 6? Let me think about it. So we had 1 6 plus 1 6. That's, no, sorry. We had 1 6 minus 3 6, or just negative 2 6, which is negative 1/3. So that's 1/3. And so now we can say our A is equal to 3/8 W, and then